So our team comprises postdoctoral research associate Barbaros Chetner and Renji Wu. They're at UCLA and UC Berkeley respectively. I'm sorry, Bingyu Zhao. And then PhD students Michael Vertusio and Renji Wu at UC Berkeley. And my co-PI in this project is Kenichi Soga. The objective of this research project is to look at the disaster resilience of a distributed network and particularly focus on bridges. Under extreme events, the resilience of a transportation network is highly dependent on the performance of its physical components, such as roadways, bridges, and culverts. And failure of these components will disrupt not only traffic, but the local economy, especially bridges. And we have focused on bridges because they are easier to model more than anything else, I suppose, in a transportation network. But it's not only that, a lot of the bridges have already exceeded their service lives. I think nearly half of the bridges in the US have exceeded their nominal 50-year service life, as you can see from this pie chart. And so the older stock, especially pre-1971 stock, is still vulnerable to earthquakes, and they have not undergone any retrofits, some of those bridges. So we want to look at a hypothetical earthquake event, a scenario-based event, and see how it will impact a particular region. And our methodology is quite similar to what you've seen from Rodrigo's presentation, but it differs in certain ways from it. We would like to develop the fragilities that are structure or bridge specific. We'd like to come up with detailed models, open seas models from street view images and satellite images and other data for every bridge involved. And then, instead of looking at the annual losses that this network will experience over its lifetime, we want to just develop first fragilities and then look at a scenario-based event to see what will happen to those bridges. And this is a mere demonstration of this overall methodology, but our application region is Southern California, and we're focusing on the ports of Los Angeles and Long Beach, which are the largest container terminals in the US, and they account for 40% of the US imports and 25% of the US exports. So, an earthquake in the region, in the area that will disrupt the transportation network will cut off these ports from the rest of the state and the nation, and then can create some cascading losses. We have a framework that comprises two segments, and they're naturally divided between the two universities. At UCLA, we're taking care of the hazard characterization and model development for bridges and calculating their fragilities. And we hand over this data to our colleagues at UC Berkeley, and they do a traffic and economic loss analysis. Their analysis combines traffic simulations, but uses data from the Southern California Association of Governments databases and traffic demand models, and comes up with detailed estimates of delays and losses in traffic. And so this is, in a way, a convergence research where two domains are interlinked: seismic hazard and loss analysis and traffic, consequent traffic and economic loss analysis. And our objective is to really go to the very end of the workflow and maybe come up with a resilience curve that shows the impact of a scenario-based event to the region and how the region may recover over time from that event. I guess if not everyone, but most of the people attending this workshop are familiar with various components of these workflows, one of which is the hazard characterization. So I'm going to skip that, but we know how to do hazard characterization thanks to the prior efforts by peers, Southern California Earthquake Center, USGS, et cetera. We have tools with which we can do probabilistic seismic hazard analysis, come up with seismic deaggregation for every bridge site, and come up with a suite of ground motions that represent the hazard in that region. And when we get these results, these ground motions, we do incremental or multi-stripe dynamic analyses to obtain the fragility curves. And at the very end, we evaluate probable damages to this network of bridges under intensity measures computed from a scenario-based earthquake. In this particular case, our scenario-based earthquake is the connected Palos Verdes fault that may produce a large earthquake, and the scenario that was previously simulated by others is a 7.3 magnitude earthquake that will happen right at the cusp of, or right at the edge of these ports, very close by. So how do we generate the bridge models? Again, thanks to support from Peer and other groups, other entities like Caltrans, we have been able to develop a software that can generate geometric models of bridges from street view and satellite images. These models can become very detailed and fairly accurate. And of course, our scheme can only generate the geometry of these bridges considered. And of course, there are other variables such as reinforcement ratios, foundation types, abutment types, etc. And for that, we rely on previous work carried out by Caltrans under the leadership of Cliff Robley in collaboration with the Georgia Tech team, who have created basically probability distribution functions for and databases for different vintage bridges, metadata, which include things like transverse reinforcement ratio, the seat lengths, all kinds of data. And we use all those data to come up with OpenSeas models. And once we have the OpenSeas models and the suites of ground motions for each bridge, we do incremental dynamic analyses and obtain IM-EDP curves and eventually fragility curves that you can see here. For example, spectral acceleration of first mode period versus curvature ductility. We can do these analyses for all the bridges in question. And then we use the ATC formulas to convert the damage data into closure data. This is a very empirical conversion, and we are just end users of these empirical formulas. And so they should be taken with a grain of sand. And this is an area where I think a good amount of research effort should be focused on to figure out how damage translates into closures, but we are using it as is from the ATC. This is a table of the damage measures and classifications we're using for different EDPs. We're looking at abutment seat displacements, curvature ductilities, etc. And then we are able to bucket our losses into 4 categories of low, medium, high, severe damage, etc. We have modeled 1,000 bridges in the region for this analysis. This may be a bit of an overkill, but we just wanted to kind of demonstrate that we could do this, this type of analysis and modeling. And of course, a huge number of these bridges have not been damaged at all from this even large event, but some did, especially those obviously are older stock, pre-1971, and those that are close to the ports and close to the fault line, fault rupture. So that's where we handed off our calculations to our collaborators, our team at UC Berkeley. And this is not my expertise area, so I'm going to just basically kind of recite what they have done in a very kind of coarse way. I hope some of our team members are in the audience, so if I get some questions, they can kind of help me answer those. But we had to our team had to first build a road network, and they have obtained it from an open source OpenStreetMap for the 6 counties that comprise the SCAG, the Southern California Association of Governments region, which include the Imperial, Los Angeles, Orange, Riverside, San Bernardino, and Ventura counties. And this resulted in a very complex, large network comprising, 600,000 plus intersections and almost 1.5 roads. So when you do traffic simulations, or rather loss of traffic simulations on this type of a network, it's very computationally intensive. And of course, our team has simulated how the traffic delays occurred in this region, for a period with snapshots of time 30 days after the earthquake, 60 and 180 days after the earthquake. And we have provided which specific bridges have been damaged and closed to traffic to our team at Berkeley and how they have recovered over time. With that information, they were able to carry out simulations of delays in traffic. And our research is still ongoing, so we are considering improvements in this. But right now, we are not able to, or not attempting to distinguish direct traffic losses to and from the ports of Los Angeles, and almost entire portion of which is comprising freight traffic, whose economic value is much different than the economic value of trips that other people take in the region. And they're interacting with each other, and delays of one type of trip are going to cause delays in another type of trip. Right now, we're not really distinguishing that in any way, but we're able to compute the traffic delays in the region, and then we can come up with at least a crude approximation for now for what may happen in terms of economic losses. So in the simulations, our Berkeley colleagues have considered 10 million trips, to 200,000 of which were originating from the ports of Los Angeles and Long Beach. This is a flowchart of their kind of workflow, and their method is a semi-static traffic assignment. And with that model, they compute for the traffic volume on the roads before and after bridge closures. And they are assuming that the vehicles are choosing the fastest path under the current road closure and traffic congestion statuses using Dijkstra's algorithm. So they can come up with maps and images like this as to what happens to the traffic, at a certain point in time since the event. These are just kind of snapshots of the travel behavior in and around the ports of Los Angeles, given these traffic or bridge closures. And as time goes by, the traffic kind of recovers. And of course, then you have accrued some economic losses during that process, which are caused by, which come in the form of both direct and indirect losses. So those are calculated right now, again, in a relatively simple way, which we are considering to make it more realistic and complex. But the overall cost is obviously going to be always a summation of direct and indirect losses. The direct losses are basically the repair and replacement costs of these bridges that were damaged. So we have used some data from the Federal Highway Administration. That is a bit dated and not adjusted for inflation, but we have used some data from them to compute these direct losses. The indirect losses are also coming in two flavors. One set is the cost due to delays, and the other one is due to connectivity. So when people are having to travel longer and more hours, then they're losing time on the traffic. And then we use that lost time and multiply it with a ratio of median household income in the US per 2,080 hours worked per year, a normalized number. And then for the losses due to connectivity, we use the annual gross regional product of California normalized by the annual labor hours in California, and we multiply that with the lost time in traffic delays. So if we wanted to do a better job, we would be looking at some coupling terms that couple both of these costs. And also we would want to specialize the second term, the gamma, to the traffic to economic losses due to delays on the freight traffic. And that dollar amount is obviously different than the amount for California averaged. But needless to say, we can still compute and go to the sort of the end of almost the end of the workflow. And according to our preliminary calculations, and please take these numbers with a grain of salt, because these are just kind of representative numbers that we want to show because we can compute them, but they're not necessarily super accurate. But the direct cost for an event like this is calculated to be like $80 million, plus the indirect costs will be about 100 million plus. So you're getting $500 million of losses in just these bridge closures due to this event. Again, a more sophisticated, detailed analysis could see these numbers go well above. And hopefully by the end of our project, we can kind of give more realistic numbers that could form some guidance to the stakeholders, owners of Ports of Los Angeles or operators of Ports of Los Angeles and Port of Long Beach, and also perhaps even Caltrans. What are we doing between now and the end of our project timeline? We would like to improve our work in both areas. One area, physical damages, the other one, the traffic simulations. In the physical damage area, we'd like to evaluate methods to define bridge damage in terms of traffic capacity reductions rather than binary open-close. We'd like to actually use site-specific GMs. We have taken a shortcut so far. We've used the peer transportation ground motion suites. And we're going to sort of redo our calculations with actually site-specific ground motion. So again, the hazard, the damages and the numbers will change. One thing that we'd like to do after that is to compare our findings, especially fragilities versus the hazardous fragilities. Ours are structure, bridge, and site-specific fragilities, and has generic ones. So what are the differences in loss estimates between the two options? We'd like to quantify and present those. And then we'd like to finalize the procedure and improve the procedure for estimating economic effects. On the traffic simulation side, we'd like to implement a more efficient algorithm to compute the shortest path. It's a computationally intensive algorithm, and our colleagues at Berkeley are using GPUs, et cetera, but still those simulations are really, really intense. And there may be ways to improve them. Perhaps even we could consider adapting neural networks to make some predictions. And of course, we'd like to also run simulations based on larger and more realistic travel demands. So with that, I conclude my presentation. Thank you.